Good afternoon, ladies and gentlemen. My name is Alexio Picco. I'm the coordinator of this wonderful consortium that is here with me, that have been working hardly for more or less 2 years to deliver the RCMS project, co-funded by the Horizon 2020 program. RCMS is about rethinking container management system. It is about an innovative robotics container handling system for port and not only port terminals. We are here together in Brussels, and tomorrow we have the final conference of the project, and we are here together to present you really the final results. So comparing to the webinar we had a couple of months ago in Copper, it is definitely the best place to be to understand better the real results that this real innovative system can deliver. We have a very good set of speakers today. Before moving to things, first, we have a number of people attending this webinar remotely, obviously. You can interact with us with the chat. You have in the GoToWebinar panel, you have the possibility to interact with the chat. So please, whenever you want, please ask questions. I would take care to manage those questions in between the different speakers or at the end. Before moving to the different speakers we have, that we will first have Anand Lepek from IAI talking more from the technological and robotic perspective of the system. Then we have Niels Kemme from APC, that is principally delivering to us the financial overview of what RCMS can be. And then moving from financial to socioeconomic the socioeconomic viewpoint, we will have Hilda Ghiera from the University of Genoa to present the cost-benefit situation, the cost-benefit analysis of RCMS. Then we have also the infrastructure perspective, in which Nico Gensten from Cellon will explain how much is, let's say, relatively difficult or complex or should be elaborated the building to accommodate the RCMS AGVs. Then we have, last but not least, again, University of Genoa, Nicola Sacco for delivering how this kind of system can impact the transport network, both at micro and micro level on the transport level itself. So to start, I think the best way to introduce the system is to start with the video. So if you could, 3 minutes video in which you can have a very nice overview of what RCMS is about. And then after the video, we will start the presentation. Please do interact with us. It's important to have your feedback and to have your questions. And this is the video. Let's see if we can also. You can see. I will see.
Yeah.
So now it's time to go into the different presentations and different technical and economics and infrastructure and everything. So first is another attack from AI, giving to us the future of vertical storage. Sounds interesting, yeah? The floor is yours, Anna.
Thank you, Alexio. Thank you for having you with us today. I'll present now how we at IAI see the future of storage, which we believe go to new places of vertical storage of containers because of the problems and challenges ports are having today. And then we'll briefly go through the different elements of the system. And from that point, then a little bit elaborating on the newly invented AGV in a little bit more details. And from that point, we will then dive in more details by HPC into the financial analysis. So we are facing, our analysis shows that we are facing increasing need for storage, and we see that in the next 4 years, this is an example for the US, more and more container terminals are reaching their maximum capacity. Therefore, we need to provide them with some technology to mitigate this risk. And of course, there are the trivial alternatives, which are building a new port, a new terminal. But not always it's easy. Not always it's a simple solution, because as you see now, the next slide shows some few examples showing that the cost of building new ports are, of course, tremendous. We're talking about hundreds of millions of dollars. This is a very costly business, and we identified that we can suggest a new technology for vertical storage, a new idea, a new concept how to store containers with less space, and then you need less areas, smaller reclamation projects. Depending on the area, sometimes it's simply not possible to expand the current terminal, and sometimes you have to consider building a new terminal. And with having the RCMS, we can suggest existing terminals either to expand using less space, or to new terminals having a much more optimized land utilization. Coming next to as we see that in the future, more and more we discuss with clients, we discuss with companies, and we see that there are more and more ideas to fulfill concepts of and develop concepts of vertical storage. We see the examples for that in Hong Kong, which actually some system was already built. We see an example for that for some concepts being developed in Korea and others in Italy. And we identify the challenges and we identify the problems with such programs. And eventually, after discussing and working with our partners in this project, in this EU project, we think we addressed very well many of the challenges, and we came with a concept called the RCMS, which deals better with all the associated challenges with regard to vertical storage. We don't have any moving elements inside the storage. It's only the robots which are moving the vehicles, the containers between the storage cells. We have a very well optimized algorithms which we developed during the course of this project, and then we implemented it and we tested it with HPC, which will maybe later on explain more about the performance of the system. So we don't have only we don't have a concept. We actually have something that we thought of the algorithms, and we developed the algorithms. We implemented them. And we see now that we have something that is very feasible in terms of technical feasibility. And this made us very happy. And then we move forward to the financial analysis, which is part of a discussion by Niels from HPC. So what we present with the RCMS is a vertical storage, automated, providing a direct access to each of the containers, which we will see in a moment. We developed together with our partners at first a preliminary design for the building. We analyzed 10 and 15 floors high, and we brought up with a concept that is an end-to-end, both dealing from the sea side up to the land side. And we have a full separation between the two. We have balconies on the sea side, dealing with the containers being received or being unloaded or loaded from the ship. And on the other side, we have what we call OHBCs, overhead bridge cranes, for the interface with the land side between the trucks and the AGVs. And all the area in between, which is number 2, is being used for the storage of containers. Each floor, we have one high of containers. This is also why we have a direct access per each container. And then on the balconies, we have the twist locks are being unloaded before unloading the container on the AGV. We will use STS cranes, which have a platform in between the legs of the STS to unload the twist locks, and then bring the container without the twist locks on top of the balcony, on top of the AGV. We have queue management on top of the balcony, and we differentiate between the loading process and an unloading process. For loading from the storage towards the ship, it doesn't matter which free AGV we allocate. We have some sort of a competition in our algorithm between the AGVs, and we have some, and then we somehow allocate the specific AGV that come not necessarily the quickest, but at the time that we best need it to be under the crane, as opposed to unload the process in which we need for when unload a container from the ship, it doesn't matter which AGV goes, and when we are loading a container towards the ship, we need to manage a specific order. And in order to do that, when we have a specific AGV coming, for example, before another AGV, then what we have is a cyclic queue on top of the balcony until so they are going in cyclic queue under the STS until the correct AGV is under the STS. When we implemented that, we also checked for if there are any traffic jams because of that concept. There were none. Everything was working very smooth. So that's as per the Site C operation and the interface. Inside we have the storage. We have, this is a top view for a typical floor. We have directions. We have a flow per each let's call it streets. We have avenues and streets. We have a very specific direction for driving. We had here a dilemma during the development how to deal with it, and we stick with the simple, which is to have one direction per each street, making it very, very simple. The number of elevators, the number of streets, the number of avenues, that would be eventually and was eventually an output from the simulation. The general layout was provided to both Celeron and HPC, and then after the simulation runs, the output was how many free lanes do we need to have in order to optimize the number of the resources, number of elevators, AGVs, etc. Inside each of the, this is how looks each of the cells is already coming from the CAD file actually, then rendered in the movie. We have direct access per each of the containers, meaning that the AGV is driving in the street, and then with a single move, it can go either to each of the sides and unload or load the container. So there is no shuffling, because in a single move it takes a container. The mechanism that we developed we developed an AGV during the course of the project, which is smaller than a single container, than a single 20 container, and it goes below the container. It has a very unique platform with the pistons, and then as you can see, it goes below the container, use the lowering or raising the pistons and taking the container, and then it goes out of the storage place. This also brings us to a better management of the locations of each of the containers, knowing exactly in which cell each of the containers is being stored. So also, as compared to other technologies, the management of all of the containers is better managed. The AGVs are deriving, as you see here, some representation for the lines on the ground. It's magnetic tapes that the AGVs are following. And this is the rendering of an AGV coming from the CAD file. It was fully designed with the mechanical teams. We had an algorithm team, software teams, and a mechanical team for the development and design of the AGV. This AGV, what you see here, are two AGVs being coupled. It doesn't matter from which side of the AGV the other AGV is coming. We have the mechanism both on both sides of the AGV, and then the AGV can be coupled automatically to carry one long 40-foot, or each of them can carry a single 20-foot. The AGVs are omnidirectional, meaning that as you saw in the movie, they can drive in either direction. We tested thoroughly the performance of the AGVs with regard to vibrations and effects on the containers, and we saw that it performs pretty well, although the velocity of the AGVs is lower than current existing AGVs, but nevertheless, in the overall performance, it didn't really matter because of the algorithms and the optimized way that we handle all of the AGVs and resources within the building. We can work for continuous 8 hours of operation with only 2 hours of electric charging. We do not sweep batteries; we charge them at some specific points. Another benefit of it is that we do not need a big facility to change batteries, because we just go somewhere and we charge the batteries for 2 hours. This is the loaded AGV with a single 40 feet, as you can see. We have the guides on the sides, which prevent the movement of the containers. It's a very light AGV compared to other monstrous AGVs that we currently see in the market, ending up with a much cheaper cost of the AGVs compared to the AGVs which are available in the market. During the course of the development, we did a very thorough work with integrating and between the interface of the control of the AGV and the physical world. And do I have the time to? Do you have the time for 2 minutes to show a video? Okay. And we show you now. This is a movie coming out from one of the design tools of the AGV. It's running actually a simulation of both the control and the physical world, and they are all interacting in between. You'll see in a moment that the movie, when it's first you see it's deaccelerating towards a full stop, and that is simulated via the control, the simulink. And when it will go downwards, you see it's not going in a direct, in a straight line. It moves a little bit sideways, and then the control is all the time fixing it. So what's important to understand is that all of that support and back the design, that now we have something that is, you can say it's really working, even though it's not existing. But using such tools, now we can actually go to building such an AGV, and we prove that it's working according to the specification, the requirements, and this simulation shows taking account sensors, motors, everything that within the vehicle, and we developed all the control that then provide us with the performance of the vehicle, which were backed by the simulation, the vehicle velocity, the speed, the acceleration in each direction. Then later on, those parameters were provided to HPC to make the overall simulation of the entire building. And then one last slide, I think, about the AGV. When comparing it to the existing ones, we see that the existing ones are really huge, with huge radius for maneuvering, while our AGV is compact, light, zero radius for maneuvering, of course much cheaper. I won't get into too much details about the elevators. It's a simple technology with cables, being able to carry 70 tons. We did a design also for that one. On the last part of the RCMS, we have the OHVZs on the other side. And here, as you saw in the movie, then we have a bunch of overhead bridge cranes. We are dynamically, with our algorithms, allocating the jobs between and the areas per which each of the overhead bridge cranes is working. And that is done dynamically according to the number of jobs that we have at a certain moment. And then we are able to send the truck to the correct parking slot and the AGV to that specific parking slot. And this was also tested, all those algorithms were also tested with the simulation, and the performance were very well. So as to summarize, we have done feasibility study. We are ready for manufacturing, because now we have great confidence in the ability to move forward. We as IAR, we are now looking for partners worldwide to go with us hand in hand to actually build the first pilot and move forward to and fulfilling what we see as our vision, the future of the vertical storage, which we believe an RCMS can have a major role in that reality. So I thank you very much.
Thank you very much, Anand. It was very interesting. So let's move to the financial perspective. Niels from APC will give us all the insights about it. The floor is yours, Niels.
Thank you. So, also thank you, Anand, for the good introduction, which is essentially a good starting point for my presentation. So having seen the basic functionalities, the basic idea of the RCMS, I would like to address the question if the RCMS is actually a better solution or than other systems. Is it more efficient than other systems? And for that purpose, we have compared the RCMS or assessed the RCMS with regards to several aspects, mostly operational and financial aspects, and compared it to state-of-the-art systems. State-of-the-art system, we consider on the one hand the RTG TTU system, rubber-tired gantry cranes, working together with simple manual trucks, so it's a fully manual system. This is of course a benchmark since it is still the most popular system in the world. And the other benchmark for the RCMS system clearly is the ASC AGV system, automated stacking cranes combined with traditional diesel-powered or electrically driven automated guided vehicles. These two systems we consider as a benchmark, and we've compared the RCMS against these two systems. And we've not just compared the RCMS for, let's say, arbitrary terminals or on a theoretical level. No, we've done it for two actually existing terminals, namely the GTK in Gdansk, Poland, and for the port of Koper. On the left-hand side, you can see the GTK from a bird's eye perspective. Here you see a schematic view of the terminal. As you can see, it's a rather small-sized terminal as compared to Koper, which is a terminal or a port of relevant size, a really big port, and also the terminal that we've developed, which is actually quite good for our comparison. So in this way, we had really two different kinds of terminals that we looked into. And the terminals also differed in other aspects. At GTK, it was a conversion. It is an existing area which has to be converted. For Koper, it was a greenfield project. So, and for GTK, since we were given a certain footprint, it is an existing terminal. The idea was to maximize the capacity of that area of the terminal, maximize the capacity for a given area. And for Koper, we were just given, let's say, an outer footprint, an outer framework with which we have to work. And however, reclamation would be needed. So the idea was to minimize that reclamation, minimize the area that's needed for that terminal by at the same time realizing or hitting a certain target capacity. So we looked into these two case study terminals and did a four-step analysis. And the first step was to develop three different layouts for each of these ports. The RTG, the RMG or ASC solution. You can see here in the top row the alternatives for GTK, for Gdansk. From left to right, it's the RTG solution, the automated stacking crane solution in the middle, and then the rightmost is the RCMS. And in the same order, on the bottom row, you can see the layouts that we've developed for Koper. And you can right away see, by the way, that the RCMS requires significantly less reclamation than the other solutions need. Following the design planning, the development of the layouts, we have modeled and simulated all these layouts in really much detail. So including all the physical equipment movements, including all business processes that are involved in such terminal operations, and also including all algorithms involved in the decision-making process for the automated equipment. Here you can, for example, see a video for the simulation of the RCMS solution for Koper. You can easily identify the vessel at the key cranes. Then you have the building, the RCMS building in the middle. We cannot look inside the building since it consists of several floors, but these are, of course, also all modeled in detail. However, you can see the AGVs moving around on the balconies. As Hanan said, they're partly running in circles, which is needed for the queue order to keep that, to respect the order of containers that is needed by the key cranes. At the land side, we have the OHBCs running around, unloading or loading the trucks and the AGVs. and we even have simulated the rail station on the terminal to take into account the movement of containers between the RCMS building and the rail station. Of course, the simulation doesn't just provide nice pictures, it also provided very helpful insights into the operation of the RCMS and the other technologies. However, we were mostly interested in the insights into the RCMS. And on this slide, we've summarized some of the most important results, namely the productivities of the involved equipment. Starting on the left, here we have the productivity of the ship-to-shore cranes, which is probably the most important productivity indicator for a container terminal, since it provides the service quality for the terminal's clients, the vessels. As you can see, the red line indicates that on average we were able to realize a productivity of about 30 moves per hour. However, it needs to be noted that we were actually aiming for a target productivity of 30 moves per hour. In practice, we have seen that by adding more equipment to the RCMS, we were actually able to yield much higher productivities than just 30 moves per hour. However, to make it comparable between the different alternatives, we stick to a target productivity of 30 moves per hour. You can also see a kind of a variation of the productivity over the course of a week. However, the variation is quite small, so most of the time we were seeing productivities between 25 and 35 moves per hour, which is essentially pretty stable compared to other systems, particularly compared to manual systems, where we see a higher variation in productivity. Looking at the other productivities, here on the right top picture, you can see the productivity of the AGV, which provides some 3.5 moves per hour, which is quite productive considering the slow speed they are moving with. On the lower left-hand side, you can see the productivity of the elevator, which provides some 20 moves per hour. And here on the right lower-hand side, you can see the productivity of the OHPCs, which are incredibly productive with some 40 moves per hour, which simply is due to the fact that they don't have to move that far. They can stay in the same place most of the time. So therefore, they're working at pretty high productivities. Based on these simulation results, we then refined our initial terminal planning, and we were able to come up with the most efficient equipment setup for each of these alternatives. So for the RTG alternative, for the automated stacking crane alternative, and for the RCMS alternative for both ports. For example, for the 15 high RCMS alternative for GTK, we identified that 7 elevators are needed, 2 OHPCs, and 51 AGVs are needed in order to hit a target productivity of 30 moves per hour at the waterside. Apart from these pure numerical results, the simulation also revealed that the RCMS operational concept, the logistical concept, is feasible as such. It is realistic. We haven't seen any big problems, any obstacles. It's doable. The simulation also confirmed all business processes and the algorithms that have been developed by AI. And I have to say, frankly speaking, I was very surprised how good these algorithms performed right away without much fine-tuning needed so far. So they were right away able to provide really competitive productivities. Therefore, I would even say that the system still includes a big potential for further improvements. So it's still an immature system, but we can spend quite some efforts to optimize the algorithms, increase the speed of the vehicle, and in this way there is easily a potential for improving the productivities of the machines by 10 to 20%. That's absolutely realistic. So in total, we can say the RCMS is operationally viable and highly efficient, which is also confirmed by some key performance figures for Koper and Dansk. On this slide, you can see, for example, some figures for GTK, for the Gdansk terminal, comparing the different alternatives, the RTG, ASC, and 2 different variants for the RCMS solution, differing in the storage height. And you can right away see that the RCMS provides, in particular with the 15 high building, by far the highest throughput capacity for the terminal. It's 124% higher than for the ASC AGV solution. Consequently, also the storage density is by far the highest, almost 300% higher than for the ASC solution. Also pretty noteworthy from my perspective is the ratio between throughput capacity and number of employees, and also here the RCMS performs by far the best. Also looking on the environmental side, we can also see that the RCMS is the best one with regards to exhaust emissions. It's clearly significantly reduces local exhaust emissions compared to traditional RTG solutions. For Cooper, we see pretty much the same results. The RCMS is best with regards to storage density, best with regards to the annual throughput per employee, and also with regards to exhaust emissions. We of course know that terminals are not just interested in providing a good operational performance. In the end, the system has also to be financially viable to some extent. Therefore, we also looked into the costs and revenues for these systems. So based on the actual cost and revenue structures for both terminals, so it's based on actual numbers from these terminals, we looked into the investments, the operating costs, and the revenues for each of these layouts that we've developed before. Considering the fact it's based on actual numbers, which are of course commercially sensitive information, we cannot reveal these numbers here. These are considered to be confidential. Therefore, I would just say some words to some key findings of the financial analysis. We can say that the RCMS equipment investments are lower than for state-of-the-art automated systems. So it requires actually lower investments than ASC AGV systems. On the other hand, construction costs are, which wasn't really a surprise, they are higher considering the size of and the dimensions of the building. However, we will see in the next presentation that the construction costs depend on several factors, mostly the soil conditions of the actual site. Looking at the operational costs, we saw that energy and maintenance and repair costs are quite similar for all systems. However, on the labor cost side, again, the RCMS leads to the lowest cost of all compared alternatives. And it clearly has to be stated that the RCMS, of course, enables a higher throughput on the given area. So it also enables higher revenues, significantly higher revenues, depending on the place where you are working. But it enables higher revenues, which will compensate for the higher costs of the building. So in totally, we found essentially that the RCMS is financially viable for both locations. We've been found a positive internal rate of return for both locations with the RCMS, and even despite the very unfavorable soil conditions, which has to be mentioned here. It's really unfavorable. Nico will explain in the next presentation that there are better locations in the world where the costs for the building can be much reduced, which makes the building or the solution even more beneficial than we've seen so far. So we can also conclude that the RCMS is not only operationally viable, but also financially viable and competitive. In summary, so summing up all the findings, we've so far just talked about costs and operations. On this slide, you can see that there are so many criteria defining or that have to be taken into account for terminals when making a decision towards a certain operating system for their terminal. We've seen that on the investment costs, the RCMS is clearly not best. On the operating costs, it has its advantages, clearly. For the operations, there are some factors where the RCMS is better, others where the RTG and the ASC solutions are better. But in total, one point clearly has to be highlighted here, the storage density. This is a unique selling point for the RCMS where no other solution can compete with. And something which has not been highlighted so far are the environmental aspects. We have partly touched the area of exhaust emissions, where we said that the RCMS is best, but it also has to be mentioned that the RCMS is best with regard to noise and light emissions, which is a topic which is becoming more and more important, particularly for ports which are in urban areas, city areas. And since the RCMS is a building, or the building is completely covered, it reduces noise and exhaust emissions significantly. So in total, I would say, to our impartial opinion from HPC, we can really say that the RCMS is actually, from our perspective at the moment, the most efficient solution to boost your terminal capacity. So I think that's a good point for the next presentation then.
Yes, if the financials are already good, you can imagine such economic benefits.
Okay,
So
the next one.
now it's your turn to go for such economic benefits.
Okay. What happened?
I don't speak Spanish.
The presentation is open.
No pudo abrir debido a que no es un tipo de archivo permitido. The file is broken. Do you have another?
Beatrice, do you have the other copy of the... Non ce l'hai sulla mail?
Io.
Ok. We've got a problem with waiting time.
Sorry, we have some technical problems. We will have to read just one new version of the file.
Just
Of the presentation.
1 minute.
Did you want me to go for this?
We have to copy it anyways. So.
Alexia? We
But
switch?
maybe we...
We switched. Okay.
Yes.
We switched. We go. Sorry.
Okay.
Me popping up again. We switch to the civil engineering part, and Nico Gerster will introduce us to the more infrastructure viewpoint. And then we move to the socioeconomic benefits later.
Thank you, Alexio. I will give a brief summary of how to build the RCMS to connect with the last webinar, and then further move on to key factors for success from a civil engineering side of view. What we see here are two top views on a container terminal area. In the left picture, we have a container terminal which is built as RMG solution, and in the right picture as RCMS solution. For the RCMS solution, the containers are stored in a multi-floor building instead of an open yard. So what I will basically talk about in this presentation is the RCMS building, how it is designed, and what the key factors for success are. One can easily imagine the basic features of such a building, which are storage of containers, of course, and the accessibility by HEVs. And what we need for that is a load-bearing system which is capable of transmitting high loads from the top of the building to sound soil, and in the same time guarantees the HEVs enough space to reach every container. The initial idea for the load-bearing concept was a grid of longitudinal and transversal beams supported by columns. Due to the high loads, which had to be transmitted by the columns, their diameter rose up to 1.4 meters, and the utilization of space in the RCMS building turned out to be inefficient. This is why the load-bearing concept was changed to longitudinal and transversal walls, which have a thickness of only 60 or 40 centimeters respectively. In addition to that, this kind of concept offers a more efficient utilization of space, an improved redundancy of bearing members, a more robust structure, and an even distribution of loads. The basic requirements which had to be fulfilled by the RCMS building are easily explained by its cross-section. The containers are delivered directly from the STS trains onto the HEVs on the balconies. The HEVs take the containers into the RCMS building and to the designated storage position. Further on, the HEVs are supposed to drive automatically through the building and on every floor. The floor height is designed for one container, and the HEVs should have direct access to every container anytime. This means no shuffling is required compared to state-of-the-art solutions. Now that we've talked about how the RCMS building can be constructed, let's have a look at some key factors for success. The aim we're trying to achieve is to store a large number of containers in small space. And what we need for that is a high building with several floors, a solid superstructure and foundation which is able to bear heavy loads. This leads us to the following key factors, which I've partially already mentioned before. The storage of heavy loads, fully automated operations, HEV serviceability, and location. In order to store heavy loads, the superstructure of the building must be capable to transmit those loads down to the foundation. Reinforced concrete is physically capable to sustain high pressures and bear heavy loads. Furthermore, it's been used over centuries, and its long-term performance, like shrinkage and creeping, is well known and can be predicted. And following the bearing system further down, it's obvious, of course, that the foundation must be capable of transmitting the same amount of loads into sound soil as well. For the sites we've been investigating in the course of this project, quite long bored concrete piles were necessary to transmit those loads. It's obvious, of course, that the soil conditions are site-dependent, and they cannot be predicted from now on. This leads as well to the conclusion that the foundation must be adapted in size and dimension. The RCMS is planned to be a fully automated system. The presence of man in the RCMS building is not allowed during the usual service. Only in case of maintenance and repair or emergencies, personnel should get access to the building. Nevertheless, the presence of personnel should be kept to a minimum. This is why staircases and elevators for persons should be installed frequently in the RCMS building. The charging stations for the HEVs should be installed in the longitudinal outside wall, so the personnel could access the charging station without entering the building. Or they even could be installed in close vicinity to the staircases to minimize the travel by personnel in the RCMS building. The reefer containers should be stored right next to the lateral outer wall, so the personnel can reach the reefer containers to check their temperature or connect them to a power supply by an outside scaffold. And as well, of course, without entering the building. In order to guarantee a smooth and proper HEV service, the floors of the RCMS building need to be as even and horizontal as possible. The largest gaps which need to be bridged by the floor construction are the avenues. They are located in between the modules of storage cells and have a span of 14 meters. Due to the long span of 14 meters, the floor construction needs a very high stiffness. To guarantee such a high stiffness, the floors should be built as composite construction, and materials like steel beams, corrugated sheets, and reinforced concrete should be used. This guarantees a high stiffness and minor elastic deflection of the floors. It's obvious, of course, if we would like to provide horizontal floors, the whole building itself must be horizontal as well. By using a deep foundation, large layers of soft and unstable soil can be bypassed. This would be the case for the site we've been investigating in Koper, where we had unstable soil up to a depth of around about 40 meters. So using a deep foundation with board piles, we even could build in such a terrain a stable building. Therefore, immediate and long-term settlements can be avoided, and an inclination of the whole building as well. The next and last key factor I'll talk about is location. It's easy to imagine that it will make a difference during the planning process if a container terminal is supposed to be located at a shallow coast with vast hinterland or at a steep coast close to a mountainside. The space available can be crucial for its feasibility. What we see here are two different scenarios for bathymetry. In the left picture, we see a shallow coast, and the right picture a steep coast, and the red rectangular represents a possible terminal area. In case of mountains close to the shoreline, it might not be possible to move the terminal area further inland. The missing land needs to be reclaimed, of course, and it's easy to see that the effort which has to be taken for land reclamation is much smaller for a shallow coast compared to a steep coast. This leads us to the following conclusion. The steeper the coast, the more land reclamation is necessary and the higher the total costs. In addition to that, if we look at the footprint of an RCMS terminal and an RMG solution, the RCMS terminal has about a footprint which is about 25% smaller compared to an RMG solution. And for the case of a mountainous region and a steep coast, the effort which has to be taken to provide a terminal area is much higher for an RMG solution compared to an RCMS solution. It even might be the case that it's not possible to build an RMG solution in such a minimalistic area. This leads us to the final conclusion that the RCMS system is a very attractive solution for mountainous regions at steep coasts. And so far from my side.
Thank you very much, Nico. Let's move now to waiting for some questions. Let's move to Linda now.
Okay. Maybe.
Hopefully. We have been running the presentation about the socioeconomic impacts and the related cost-benefit analysis. So let's see if the floor is yours.
Jan 2007.
Not yet here.
Not here? Not here? Not lucky today. January? This is
2017.
final conference. Okay. Okay, it's okay. Is it okay? Or... Okay, thank you so much. Okay, perfect. So, after the presentation of the financial analysis from HPC, we will discuss now the economic appraisal of the RCMS project. I will give you a short description of the framework and the general background. Then I will present the analysis structure and development. We will discuss the main issues of the cost-benefit analysis, and then we will see in details the case of Copper and the case of Dansk, the two case studies taken in consideration in our analysis in our project, and then I will give you some final consideration about our work. I would like to remember for the not expert people that a cost-benefit analysis is something quite different from a financial analysis, because in this case we have an infrastructural assessment in which the economic and social values substitute in some way the cost and revenues in order and with the aim to understand not the financial viability that we discussed before, but the overall net benefit for the local community that will host the port and the infrastructure. So we have a quite different perspective from a financial analysis. The aim of the analysis in a general way is to provide, in the case of the RCMS project, a comparison between the RCMS solution and the two competing technologies already discussed with Niels, that is the RMG and the RTG solution. The economic analysis took place during the overall project duration, but we can identify three main steps that we developed. Of course, the definition of the theoretical background, we have to underline that in the case of port, we have quite different problems for a cost-benefit analysis, because we have a specific condition. Port is a very particular infrastructure, so different from other cost-benefit cases. We need on-field data collection, of course, with the partnership and with the partners. We tried to collect detailed information on the context, because every cost-benefit analysis is a very specific and local experience. And the third step, of course, has been the evaluation on one hand, and on the other hand, another very important issue, that is the sensitiveness study, in order to check the impact of the different items taken in consideration during the analysis. The main tool used in a cost-benefit analysis is the ENPV, the net benefit of the infrastructure. Another very, very important point is that in this case, as in other cases in the cost-benefit analysis, it's very important to discuss, first of all, the assumptions and the hypothesis chosen to develop this specific analysis. In our experience, the first item to underline is that we choose a discount factor of 5%. And this is, of course, a critical element. This discount factor of 5% has been used as a base scenario for the analysis, but consideration including alternative scenarios, specifically the 10% discount scenario used in the financial analysis, have been included in the analysis. Another very important point is the period, the reference period. In this case, the reference period is set at 25 years, but also in this case, we take in consideration another alternative scenario of 20 years, because this was the reference period for the financial analysis, so we have the possibility to compare. Another point is that an environmental impact assessment has not been implemented in the case of the RCMS project. And so environmental hypotheses, more general, have been used in order to point out some specific environmental impact of the project. The financial data and the externalities hypotheses are in a general way based on previous deliverables. So for cost and revenues, of course, the financial analysis, and for environmental impact, we used the results of the model that will be presented by the other part of our university, the engineering. Concerning the targeting market, general information has been discussed with the different case studies, so the different ports, in order to have a realistic hypothesis on the targeting market. So it's important to underline that the analysis compares the different terminal layouts that have been presented before and the performance characteristics due to the competing technologies. On one hand, the RTG, on the other hand, the RMG and the RSCMS, discussing, as I said before, the effect on the benefits, but the general benefits on the community, and these benefits are both monetary and non-monetary. So, of course, one of the main aims of the analysis is to translate the non-monetary costs in money. And on the other hand, we have the costs who are mainly monetary and based on the financial analysis. At the end of the comparison that I will sum up in the next few minutes, we decided to elaborate a discussion of the elements that are normally included in the CBA, that have been prudentially excluded in the proposed economic analysis, but that are discussed in a general way. Talking about externalities, were one of the main elements of the analysis, accident and air pollution represent the main considered factors, but maybe during the question period we will have the possibility to discuss more in detail this element. So you can see now in the graph the results for the case of copper. You can see the net discounted benefit, the ENPV value, and we can say that the project, as we know, the project in copper aims at building a new terminal. So we have two different case studies. In the case of copper, a new terminal. In the case of Danske, an upgrade. In this case, all the technology will allow the achievement of the same targeted throughput. And it will take a few years before achieving this target. In the analysis, we decided to plan 1 year for the 50% of the target, 2 years for the 75% of the target, and 3 years for the 100% of the target. As we can see on the graph, the main costs are focused in the first 3 years, while the main benefits will begin from year 3, and we have an important period in years 15 because we need an upgrade of the equipment, so we have to face some other costs during this period. So here you can see the preliminary results of the cost-benefit analysis in the case of copper. As you can see immediately in the table on the right that sum up the results, the ENPV for the RCMS is the highest in the case of the discount factor of 5%, that is the base scenario, but also in the other scenarios, that is with the 4%, 7%, and 1% of discount factors in the case of the RCMS. On the left, we have another figure describing the sensitiveness of the ENPV, so the net value, to the discount rate variations. And we can see from this graph that the RCMS registers higher ENPV for all the discount rate lower than 14%. And this is another very important result in the case of copper. As I said before, a very important step for the analysis, for the cost-benefit analysis, is the sensitiveness analysis. In this case, it shows that RCMS is impacted mostly by externalities. As I said before, we are talking about air pollution and traffic flow and modal shift in the case of the overestimation, but it results the RCMS the best option in the copper case anyway. The figure on the right shows the case in which an increase of 20% of the investment cost occurred. So we have a mixed shocks scenario with an increase of 20% of the investment cost, together with a decrease of 10% of the revenues and 20% of the external benefits. So this figure is very important because it answers to the question, what will happen if we underestimated some items or overestimated some other items, for example, revenues. In general, we can see that of course, always mixed shocks bring to different outcomes in a general way. Nevertheless, in this case, RCMS seems quite resilient, quite robust, also to heavy modifications to particular cost-benefit items, while, as we can see on the right, the RMG and the RTG, that is the other two systems, register higher fluctuations even for marginal mixed change. And you can see the RCMS register higher ENPV for discount rate lower than 10%. So this is another very, very important element in the analysis. Now you can see the results for the case of Danske. As I said before, the project in Danske aims at expanding the current existing terminal, so it's something different from copper. In this case, the competing technologies will allow the achievement of different target throughput that will bring to different modal split and rail transportation capacity. And this is very important when we talk about externalities. Also, in this case, the main costs are linked to the implementation of the infrastructure, of course, and are focused in the first 3 years, while the main benefits will begin from year 3. Also, in this case, we have some consideration about year 15, because we will have some equipment upgrade. So also in this case, we can give some numbers, some figures about the results. In this case, as you can see, we can take into consideration the 5% discount rate, and we can see that in this case the ENPV for our CMS is not the highest, because the RMG is better in this case, but it's the second one, and the same situation is also for the other scenarios. In this case, we have to underline that RCMS registers the second highest ENPV for all the discount rate lower than 12%, as you can see in the graph on the left. So this you can see the sense of a cost-benefit analysis who underline, point out the different situation and the different evaluation of the system for different contexts. As I said before, also in this case, it's very important to focus on the sensitiveness analysis. In this case, as well, the RCMS is impacted mostly by the externalities overestimation and also by the investment costs. Nevertheless, the other solutions are more sensible than the RCMS to the high cost benefit variation. Also, in this case, we are showing a case in which we have an increase of the investment cost together with a reduction of the revenues and externalities. So also in this case, we are answering to the question, what will happen if we have an overestimation of the revenues or underestimation of the benefits. And we can see that for values of about 9%, the RCMS account for comparable ENPV value with RMG, while for discount rate higher than 9%, the RTG registers higher value. In general, of course, also in this case, the mixed shocks underline that both RCMS and RMG seem quite resilient, seem quite robust. So we can confirm a very important point that RCMS is the best solution for copper, is the second solution for Danske, but in both cases is very, very resilient to change in revenues and in benefits. Some final consideration, as you know, in a general way, a cost-benefit analysis cannot be generalized. This is linked to the aims of the cost-benefit analysis, but we can say that in a general way, RCMS registers positive impacts for every operational externalities that a terminal can generate, e.g. emission, noise, pollution, etc., or influenced by the transport flow. So you can see on the left these negative, we can say, this element. And we can say, on the other hand, that every element related with the construction of the main building is normally associated with a negative effect on the ENPV. For example, landscape, soil characteristic that we discussed before, and so on. Of course, so we can in some way generalize the cost-benefit analysis results, but in a very, very general way. Of course, in future analysis, we will take into consideration also other impact, for example, land reclamation and so on, that can have a very strong impact on the analysis. Of course, the level of sensitivity of this general consideration depends always on the local context. If I have a few minutes still, I can say, no, it's too much? Okay. Okay. We have to underline that the economic analysis has been developed in a very prudential way, so we decided not to take into consideration a lot of externalities that, as the land reclamation, that can be very, very important in the case of RCMS. But nevertheless, RCMS appears as the best option in Cooper and the second best in Dansk, also in the case of very prudential approach. The main strength of the RCMS solution, of course, are related to the better flow organization that we will discuss now with the Faculty of Engineering, and the better ratio performance space required that assure higher net benefits, and this element has been shown by Nils before. Of course, in a general way, local situations and the characteristics seem to affect the achieved results, but nevertheless, RCMS is, as I said before, quite resilient and robust to the change. So, in summarizing, good results also for the cost benefits analysis. Thank you.
Thank you very much, Hilda. We go for the very last one, but not least, the impact on the transport network from the micro and micro perspective. Not more than 3 hours. Yeah.
Okay. Where the presentations? Okay. I will try to be short.
Give it a try.
Okay. In this talk, I will show you some results, a glimpse of the results about the effect that RCMS can have on the transportation network. The first consideration we have to do is that a seaport, as any other logistic terminal, is not an isolated system. It is a node of a network, of a transportation network, and the connection between the different nodes has to be taken into account. So the idea was to assess the impacts on the transportation network, provided that RCMS is inserted in a single or in one or in more than one terminal. More in detail, we had an estimate of the effects on the land-side transportation network, in particular on the modal shift on a large scale, scale in the sense of regional or European scale, and an estimate of the impacts on the local urban traffic network. Basically, the analysis consisted in the realization of 2 models. The first on the left represents what we call the global model, whose aim was to understand if there is the possibility of driving a modal shift from truck transportation of freights towards rail transportation, which is known to be more sustainable. On the left, we have the local model, whose aim was to understand which are the impacts on the urban level near the seaport. The 2 models are connected in the sense that if we are able to move some freights from trucks to rails, we can reduce the congestion level in the local area. We have to take into account that most of the European seaports, at least, are near or inside the cities. So any reduction of the truck flows has potential benefits in the congestion, in the livability of the cities. The model was developed by considering the third port involved in the project, which is La Spezia seaport. We concentrate our analysis on this seaport because also the municipality of La Spezia was participating at the project and provided the private traffic data, which are necessary to understand the interaction between how normal users, citizens that live in La Spezia, interacts with the freight flows that come or go to the seaports. La Spezia is a medium-scale seaport characterized by 1.3 million TEU per year, and more or less there are half and half import TEUs and export TEUs. What is interesting to know that it is in effect very important from the point of view of the analysis is that most of the relation of the seaport, the origin-destination relation of the seaport, are characterized by a quite high rail percentage because this seaport is very well organized and vocated to rail transportation. So we have even a case, Veneto 1, which is characterized by more than 60% of rail transportation percentage. Other destinations, the most near to the seaport, are characterized by 100% transportation, but it is reasonable because of the distance. In this scenario, we consider the present case, that is the present modal split, and the present costs, and the present estimation that users have about the cost and the port and the comfort and the performances of rail transportation and road transportation. Based on this estimation, we have built a model to forecast what happens in a future scenario. We consider an increase of throughput and capacity around 35%, which is the one which is promised, more or less promised by CMS. In this analysis, we consider basically three scenarios. The present scenario, which is characterized by a low automation level, which involve some manual operation and, of course, some automation, but man-operated ones. Then we inserted RCMS only in the origin seaport. We consider what happens if only a Spezia is characterized by the presence of RCMS, and what happens if even the destination of the relation of the seaport are also characterized by RCMS. Of course, reducing the cost in the origin and reducing the cost both in the origin and in the destination provide different results. The output of this analysis was the modal split. That is the percentages of trains that choose road transportation or rail transportation. Here are some of, it is just a glimpse of the findings. It is a case of medium distance relation, which is characterized by high percentage of road transportation. It is the red one in both the picture, and in particular, the actual split is depicted by the dashed line with the circle. The future scenario are characterized, as I said, are characterized by only RCMS in the origin, which is the star one, the dot and the star line, and the last one is the continuous line with the circle, which is characterized by RCMS both in the origin and in the destination. We can see that in a horizon of 10 years, these percentages can change a bit. In particular, we have that the percentage of rail transportation increases if RCMS is in the origin and destination of about 10%. On the right figure, we have more or less the same analysis, but we are now considering the import flows, that is, those coming from Piedmont and directed to La Spezia. The findings are more or less the same. Summing up all the OD pairs characterizing La Spezia, we have more or less an average modal shift of about 20%. That is, meaning that the potentiality of RCMS is about moving from the road to the rail about 20% of the freight. The last analysis we provided was, as said, understanding what are the impacts on the local network. To do so, we consider both the private traffic around the seaport and the traffic generated by the freight traffic generated by at the gates. In this graph, we reported the increase of delay time. It is we choose the delay time because it is a performance measure that all of us know very well, because all of us are more or less drivers. For different origin-destination pairs inside the city, we have a significant increase of the delay due to the interaction, due to the high level of congestion generated by the growing freight around. The light, in particular, the light bars represent what happens if the throughput and capacity are increased by not using RCMS. That is, for instance, by land reclamation, by increasing the yard, by something else. On the dark green bars represent what happens if we consider the same increase of freight, but mitigated by the modal shift. In this case, all of the relations are characterized by lower levels of increase of delay. Evidently, the delay time increases anytime, because anytime we have most vehicles around, the delay time is the congestion increase and delay time do the same. What is important to note is that if our target, if the seaport target, is to increase the capacity, it can be done by mitigating the effects on the land side. This analysis, together with the related analysis of pollutant, of noise, and also accidents generated by the new traffic, can be considered in a more general framework that takes into account that what vehicles generate in terms of pollution is saved by, for instance, by the engine system inside the seaport, which is basically electrically powered. So from the global point of view, from the city point of view, what is an increase in traffic can be a saving in the seaport. So the balance can be positive, but it is a matter of other analysis than that. Just to summarize the analysis, increasing the capacity by RCMS, that is basically raising the automation level with respect of other possibilities, leads to a reduction of the cost and time of a load and load operation. This comes from basically because most operations are more reliable, and the congestion effect inside the terminal is reduced. It is translated into a modal shift towards more sustainable transportation systems like the railway one, but it is important to take into account that RCMS has the potentiality of drive a modal shift, but the rail transportation network inside the seaport, but also outside the seaport, has to have the capacity to absorb the increasing number of trains. Otherwise, anything we can do inside the seaport is not significant for what happens outside. I finished. I was very short.
It was very much on time.
We have just finished. It seems that we definitely were more clear than the first time, in which more questions were coming from the panel. We got nearly 20 people, more or less, like attendees, like last time. So I think we can close here the webinar. We are a little bit late, but 1 hour and a half, I think it's the time that is needed to present all the results we got so far. The webinar will be uploaded on our website. So for whoever wants to have a look further, this is an opportunity. And of course, tomorrow we have the final event of the project, in which more people will attend, and in which basically we are going to have some external guests, but from the department side, we are going to do the same presentation of today. So thank you very much to all of you, and hopefully we will have other webinars concerning RCMS or development core concerns or concepts coming from the RCMS in the future. So thank you very much, and Have a nice afternoon. Thank you.
Now we can speak freely again. So shut down.